Hey there, and welcome. You know those arrows you see in math or physics class, the vectors? Ever feel like they're just a little abstract? Well, we're going to fix that today. We're going to break them down into their super simple core parts. And I promise, by the end of this, you won't see confusing arrows anymore. You'll see a crystal clear recipe for a journey. So let's dive in. So here's our game plan. First up, we'll figure out what exactly we're even trying to describe. Then, we'll set up our map. Gotta have a map, right? After that, we'll see how to break the journey down into easy pieces, meet the little guys who give us direction, and then, boom, put it all together. It's a super clear roadmap to getting this stuff down cold. All right, let's kick things off with section 1. So, what are we describing? I mean, what's the whole point? It's really all about one thing: turning a fuzzy idea, like just saying, go over there, into a perfect, totally precise instruction that a computer or a physicist could understand. So, let's get into it. Imagine you found an old school treasure map, and the X that marks the spot is kind of diagonal from where you are. Now, how do you give someone perfectly clear directions to get to that treasure? You can't just point and say, it's kind of over that way. I mean, that's not going to work for math or physics, right? We need absolute precision. Okay, so if we're going to give perfect directions, it's pretty obvious we need a perfect map to work with. That's our foundation. And that brings us right into section 2, setting up that map using the awesome power of the good old XY grid. And guess what? This map is something you've definitely seen before, probably 1,000 times. It's just the simple XY coordinate system. Yeah, like the graph paper you used in school. Just think of it as the grid that's drawn right onto our treasure map. You've got the x-axis that goes left and right, that's our east-west, and the y-axis goes up and down, that's our north-south. It's simple, it's familiar, but trust me, it is incredibly powerful. So on this brand new map of ours, what's a vector? Well, it's just an arrow, that's it. It represents that diagonal journey to the treasure we were talking about. It starts right at the center, we call that the origin, and it points straight to where we want to go. Now here's the really crucial part. Every single one of these arrows has two things that define it: how long it is, its length or magnitude, and which way it's pointing, its direction. Okay, so we've got our diagonal path, our arrow, but trying to describe that single diagonal move, it can be tricky. And this leads us to the absolute core idea of this entire explainer. We're not going to do it in one go. Instead, we're going to break that journey down into much, much easier steps. Think about it like this. Instead of telling your friend, hey, walk 5 miles northeast, which is kind of hard to follow perfectly, what if you said, okay, first walk exactly 4 miles east, then stop, make a sharp turn, and walk exactly 3 miles north? Guess what? You end up in the exact same spot. We've just swapped one tricky instruction for two super simple ones. And right there, that's the big reveal. Those two simple instructions, the how far east part and the how far north part, they have a name. We call them the vector's components. That's the word. They're like the individual Lego bricks that snap together to build the whole diagonal vector. And here's a really cool way to think about this: the shadow analogy. Picture this. You've got your vector arrow floating there, and there's a bright light shining straight down from the ceiling. The shadow that arrow casts on the floor, on the x-axis, that's your x component. Now imagine another light, this time shining from the far right wall. The shadow it casts on the left wall, the y-axis, that's your y component. It's so cool because those two shadows tell you everything you need to know. Okay, this is great. We've got our two numbers now, right? We know how far to go sideways and how far to go up. But wait a minute. In the language of math, how do we label one number as the sideways one and the other as the up one? For that, we need to call in some special helpers. It's time to meet the direction givers. And this really is the key question, isn't it? We have a number, let's say it's 4, for our horizontal piece, and another number, 3, for the vertical piece. But how do we make sure nobody gets them mixed up? How do we, glue the idea of horizontal onto the number 4 and the idea of vertical onto the number 3?
Well, the answer is this brilliant, elegant little tool called a unit vector. So, what is it? A unit vector is basically a tiny, perfectly standardized arrow. Its length is always, and I mean always, exactly one. It has one job and one job only: to point. That's it. It's just a little signpost that says, go this way.
And for our 2D map, we have two absolute superstars. First, there's E hat. We often call it I hat because of the little hat on top. Its only job is to point perfectly along the positive x-axis. It's basically screaming, hey, the number next to me is the horizontal one. And then you've got its partner, J hat, or J hat. And you can probably guess its job. It points perfectly along the positive y-axis, telling you, and the number next to me is the vertical one. And that's really all they are. They're just labels. They're tags. The moment you see a number with an I next to it, you know instantly that's an X direction number. The moment you see a number with a J, you know it's for the Y direction. Problem solved. No confusion whatsoever. Right, we've got all the pieces now. We have our ingredients, those are the component values, the 4 and the 3, and we have our labels, the I and J, to make sure we know which is which. It's time for the grand finale, Section 5, putting it all together to write out the complete recipe for our vector. Let's actually build it step by step. It's super easy. First, you take your X component, your horizontal number. Let's stick with our example, so that's 4. And you just stick the I right next to it. Boom, 4I. Then you grab your Y component, the vertical number, which was 3 for us, and you attach the J. So now you have 3J. And the last step? You just put a plus sign between them. Our complete vector recipe is 4I plus 3J. And that's it. Look at that. That one simple expression is the whole shebang. It's the perfect recipe. It tells you everything. Both the length and the direction are baked right in there, all broken down into 2 simple, easy-to-follow instructions. We've totally solved the problem we set out to fix at the very beginning. We now have a perfect, mathematical way to describe that diagonal journey. So, before we wrap up, let's do a quick recap of the key takeaways. Here's what you really need to remember. 1. Any diagonal path, any vector, can be broken down into a simple how far sideways and how far up and down part. We call those components. 2. We use these special little pointers called unit vectors, I and J, that are just labels for the X and Y directions. And 3. When you put it all together, you get this perfect little recipe that describes any 2D vector. And that leaves me with just one final question for you to chew on. We've totally mastered the 2D world, right? The flat map. We have our X and Y axes and our direction givers I, J, and J. But what about the real world, the 3D space we live in? What extra piece, what extra direction giver do you think we would need to describe a vector that not only goes left, right, and up, down, but also comes out of the screen towards you or goes into it? Something to think about.